Hello and welcome to today's webinar presented by Deluval Software. Today we'll be working in our structural analysis and design software, RFEM. The topic for today's presentation is ACI 318, 2019 Concrete Design in RFEM 6. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the US office and also a technical support and sales engineer, and I'm located in Philadelphia, Pennsylvania. My colleagues Alex Bacon and Siska Choa will also be joining me as your moderator, answering any questions you may have. They are both technical support engineers, also located in the Philadelphia office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the presentation. You can do so within this same dialog box. If by chance we don't get to all your questions, we'll certainly send you a follow-up email afterwards. As far as the content over the next hour today, we're going to move through a couple of examples, and we'll be working in our new FEA program, RFEM 6, as well as utilizing the concrete design add-on. So I'll give you a quick introduction to concrete modeling within our program. We'll take a look at reinforcement data input for both members and surfaces. We will be running an analysis and of course design according to the ACI 318. And finally, at the end, I'll show you a few printout report options that are available within the new program. So we'll actually begin immediately within RFEM with our first example. So when we begin a new file, we want to give it a model name. The type of model is set to 3D. On the second tab, you'll notice here are all of our add-ons. So these add-ons would only be available if you've purchased them. And today we'll be focusing on the concrete design. You can see I've activated it here. Under the third tab, standards, this is where we can select the relevant concrete standard since we've activated that add-on. Today we'll be working with the ACI 318, but you can see here the Canadian standard, the Eurocode, and other international standards are available. As far as our load cases and combinations, we'll be working with the ASCE 7, but of course we can use our drop-down to select a different standard there. And finally, under the settings and options, this is where I can orient my global and local axes. You can see I've set both of these Z axes to upward for the model here. So once we are done defining this basic information, we are brought into the main program RFEM here. And we want to start off with our drawing grid, which we can right click at the grid down at the bottom to edit this. You can see that I have my grid point spacing set at 1 foot. If you have anything else here, you can either reset it or you can choose this option here, default. That will move it back to 1 foot on spacing. We want to begin by defining a new material here. So we will right click within our navigator under the material to create a new material. This will bring open our dialog box within the program. We can then access our material database and we'll take advantage of the filters over here on the left. So you can see within my drop down, I can choose concrete, I can select the standard ACI 318 2019, and from here I can choose my 4000 PSI concrete. Notice on the second tab here with this concrete material, we also have the settings for creep and shrinkage. This comes into play a little bit later on with the serviceability design for long-term deflection if we wanted to consider that. We'll go ahead and leave this unchecked for our example today. Now, while we're still in this dialog box, we want to create a second material. So we once again visit our material database, and over on the left, we use our filters to reinforcing steel. Again, selecting the ACI 318, we can now choose grade 60. So this is a little bit different in RFEM 6 than what we saw previously in RFEM 5, where we do want to go ahead and define that reinforcing material here for our concrete elements. Once those materials are defined, we'll see them over here within the navigator tree. Now we want to do the same thing for our first cross section. So I can right click on the section here, go ahead and choose new section. And we'll see some of the various massive shapes available to us on the right. We can always visit our database here to choose from the library the various thin-walled and massive cross sections. We also have all of the available sections from the steel standards, aluminum, and so on. But sticking with this basic rectangular section, under the second tab here is where we can go ahead and modify these dimensions at 12 by 18. The third tab will, of course, calculate all of the cross-section properties for us automatically. So we click OK, and now this section is available to us, and we want to begin by drawing our first member. So I can go up here to my toolbar to draw a new single member. And what you'll see here is the member type is set to beam. Now notice the design properties is automatically checked on here. This is all related to that concrete design add-on that we activated within the base data. When we have this unchecked, notice all of these tabs disappear up here at the top related to our reinforcement. We will only perform an analysis if this option is not checked. But of course, we're also interested in the design portion for our example today. So we'll go ahead and leave this turned on. We'll get back to some of these various tabs here in just a minute, but starting with the basic geometry here, I'm going to snap from my point 0, 0, 0, and my second point will be at 26, 0, 0. So we have our first beam element shown here. Now I want to add a node along the member length here. So I'll right click on the member, and under members, we have the option here to divide the member by a distance. Within this dialog box, I can tell the program to go ahead and place that intermediate node 20 feet from the member start. But rather than dividing the member itself, I can choose this option down here to actually create the node without dividing it. So it will remain one continuous segment. I click OK. I can turn this into wireframe view, maybe turn off my grid. I can zoom in here and you'll see this node added along the member length. So let us continue on by supporting this simple beam. So we'll go up to draw a new nodal support. And we have some default options within the program here, such as a typical pin support, maybe a typical rigid. We can also create a new support definition. So within this dialog box, we have our 6 degrees of freedom, 3 in translation, 3 in rotation. Now we also have partial fixity. So if we have something that's not fully fixed, not fully released, we can go ahead and define that spring constant there. And lastly, because RFEM is a nonlinear program, we can define these geometric nonlinearities for the nodal supports within our third drop-down box here. For our first nodal support, we want to restrain the rotation about the global x-axis, which I can see back here in the background. I click OK for that first definition type, and then I can graphically select my node here, node number 1. Now notice I'm still within this dialog box. I can click Apply, and I can create a new nodal definition once more. This time we're going to release the translation in the global x direction for a roller. I click OK. I can graphically select my intermediate node here, and I click OK once again, and now our nodal supports are shown here at both these nodes. Now, something new that we've added within RFEM 6, you can always right-click at one of these nodes and take advantage of this slider option to increase or decrease the size of those nodal supports. Okay, so now that we have the basic geometry defined, let us move on to loading. Now notice the program has already created one default load case here. So if we go into this option, Edit Active Load Case, we can go ahead and rename the load case dead. Now the self-weight is automatically activated here. The action category is set according to the ASCE 7 to dead load. So for our second load case, we will create this as live 1. The action category will be set to live. The self-weight will be automatically unchecked here because we don't want to account for it twice. And finally, for my third load case, I will make a copy and we'll just simply rename this one live 2. So now that all 3 of our load cases are defined, I want to take a step back here under the first tab base. We will generate those load combinations automatically according to the ASCE 7. Remember, this is what we set under our base data, but we can go ahead and make a change to a different standard here. I also like to activate this option, the combination names according to the action category. Under the actions, we have both dead load and live load defined. Because we have 2 live loads under our load cases, we need to tell the program how to combine these within the load combinations, whether that's together or separately or alternatively. So we can choose those options from the drop-down box here. Then we have our design situations, and this is new within RFEM 6. So we have 2 design situations created, and these will be used for our concrete design. Notice we have LRFD for our factored load combinations and ASD for our unfactored load combinations. Both of them are active here for the concrete design add-on. Now, if we're curious to see what these load combinations look like, referencing the standard, we can click on this little info button here, and now we can see all of the load combinations in detail. But there's something that we need to also take care of within this combination wizard here that's important for concrete design. And for our factor load combinations, which will eventually be used for our strength limit state design, we know that we need to apply this I crack factor that comes directly from the standard to reduce the stiffness. And that's all done here within the combination wizard. So I can go to the edit settings here. And notice the static analysis settings is set to a second order analysis with P delta considered, which is great. That's exactly what we're going to be utilizing today. But we also want to turn on this option down here to consider the structure modification. Now I need to create a new structure modification. I'll activate this for members since I only have one member in my simple model. And within my tab that appears here, I need to use the drop-down box to create a new member stiffness modification. And sure enough, within this drop-down box, we see here the ACI 318 table 66311A listed. This is just going to reference the code to give you the I crack factors for the various component types here. And for today, we obviously have a beam. So the I crack factor of 0.35 will be applied to the bending stiffness here. So I can click OK here, and then I'm going to want to either type in my member number or I can graphically select it. I click OK, and now for my factored load combinations, the I crack factor will automatically be considered. But when we're talking about our unfactored load combinations for serviceability design, we do not want to apply that I crack factor stiffness reduction. Rather, what we reference here from the code is the effective moment of inertia, I sub E, from table 24235. So we actually need to deactivate that I crack factor here. Well, that's easy enough. If I go into my combination wizards and create a new definition here. So previously for my factored load combinations, I was using item number 1 here with my structure modifications active. Now for my third one that I just created, we want to choose a second order analysis according to P delta, but I will actually leave this turned off. The concrete design add-on is, we'll go ahead and determine the effective moment of inertia I sub E for deflection calculations automatically. So nothing needs to be done here with serviceability or deflections for the ASD design situation. We just simply need to deactivate those settings here under that third definition. So now under the load combinations, we can see here our factored load combinations in orange, and notice the structure modification, that I crack factor, is applied to these. Our unfactored load combinations here in red, this setting is turned off. So now that we have defined the load cases and combinations, we need to actually apply the load to the member. So we'll start off with a new member load within our toolbar here. The program asks us which load case to place this member load under. We'll choose dead load. And up pops our dialog box where we can simply define the load magnitude of negative 1.0 kip per feet. And this will be applied along the full length of the member. I can graphically choose this member or type in member number 1. I hit apply and next. And notice in the background that load was applied, but I'm still within this dialog box. What this allows me to do then is to drop down to load case number 2. And I'm going to change the load distribution here to trapezoidal. And I'm going to adjust my load magnitude at the start of negative 0.2. The end will also be negative 0.2, but I want to make sure to apply this only from point 0 to 20 feet on my beam. I go ahead and type in member number 1, apply and next, and in the background we should see that live load applied only between our 2 nodal supports. And finally, we want to do the same thing with load case number 3 here. We're going to leave the load magnitude the same, but we want to adjust this to 20 feet and then to 26 feet. We go ahead and hit member number 1 here on our keyboard. I click OK, and now we should see that additional live load defined here. Now within my drop-down box, I have the ability to cycle through these different load cases and combinations to view the loads applied to my beam, also including the load factors from the ASCE 7. Okay, so what we can do now is to choose this LRFD design situation, and I actually can run a quick analysis. So remember, I haven't modified my reinforcement yet. I'm not really doing the design quite yet according to the ACI. The program put in some default reinforcement to begin with. But looking at just these static analysis results, notice we have a new tab here within our navigator, and it's grayed out because it's the only thing that we've solved for, but it says static analysis. Now we're probably not so interested in the global deformations for these factor load combinations, but what we can take a look at are topics like internal forces. And you can think of these design situations as an envelope solution. It's going to group together all of those factor load combinations. And what you'll see here are 2 different values for all of my internal forces. Well, these 2 different values just refer to here the envelope values. And currently I'm viewing both the max and min, but I can set this to only the max or only the min, and then we'll see that adjust here graphically. We also can display, of course, the support reactions. Again, these are just the internal forces. This is probably what we'd want to use then to do our design according to the ACI. So moving on to that topic, let us double click on this member to explore these other tabs located up here at the top for our reinforcement definition. The first tab is the concrete effective lengths. I'm not going to touch anything within this tab. The reason why is because when we do not do anything within this tab, it is going to design the member according to a P-delta analysis. That is one of the approved methods within the ACI standard. Now, alternatively, if I do define an effective length within this drop-down box, it will design according to the moment magnification method. And again, this is also from Chapter 6, an approved method. But we'll go ahead and design according to P-delta today. Therefore, under our concrete cover, we can leave this as 1.5 inches, which is default here. Our shear reinforcement. This allows me to define different zones if I want along the member length. So notice I can create these different zones here and adjust my shear reinforcement as needed. Now, for our example today, what we'll do is just go ahead and utilize these number 3s, but I'm going to modify my spacing at 0.5 feet or every 6 inches. And notice this picture down here automatically updates with my shear reinforcement. Now this is applied along the full member length. Under my longitudinal reinforcement, this is where I'm going to set the longitudinal reinforcement as shown over here in this graphic, this cross section. I can go ahead and use my drop-down box to choose unsymmetrical. Well, this option now gives me the ability to define 2 number 5 bars at the top of my beam. We can see that picture update here. Along the sides, I'd like to define 1 number 4. Again, seeing those lateral bars here, go ahead and update in the picture. And then finally, we want to update the bottom. We'll go ahead and choose 5 number 5s from my drop-down box here. And we see those 5 number 5s shown within the cross section. So this is going to be applied along the full length of the member here. And what else we can do is to define a little bit more information such as reinforcement offset, but also anchorage type and at the start and member end. This is all going to come into play for our development length design checks within the ACI, so we can make adjustments there. For now, I'll just go ahead and leave this as empty. Now, we of course have some additional positive bending moment in between these 2 supports. So perhaps this reinforcement isn't completely adequate, and we'd like to add some additional bottom reinforcement only at this location. So what we can do here is to create a new item. And up at the top, I'm going to choose from my drop-down box here the option D line. Then I'm going to choose 4 number 5s. Then I want to adjust my offset distance. So this is all measured directly from the stirrup. And we can go ahead and modify this at 0 and 1.7. And then for the right-hand side of this line reinforcement, it will be 0 and 1.7 again. Okay, so now we see that additional reinforcement, but right now it's shown along the entire length of the member. I'm going to actually modify this to begin at 3 feet and it will end at 17 feet. And now we can see the reinforcement shown here, which will coincide in between the two nodal supports. Now, similarly, we probably have a negative bending moment over this intermediate support here and into the cantilever portion. So we'd like to add some additional reinforcement for the top of our member. So let us once again define here the option D for line. And we're going to choose here 2 number 5s. Now, for this option with our offset distance, we want to use the drop-down box here to choose center, top, positive Z. Then I'm going to modify my offset distance to negative 1.2 and 0. I'm going to choose the same option here, center, top, positive Z, and this is going to be 1.2 and 0. So now we can see that additional reinforcement at the top shown here. Now we don't want to run this along the entire member length. Rather, we are going to choose a distance here of 17 feet to 25.5. And now we have the additional top reinforcement defined over that intermediate support. So that will be all that's needed for this particular tab. So we'll move on to design configuration. So we have strength configuration and serviceability. Both come with a default option. We can go ahead and edit the settings for this default. What you're going to see here are just the various options specifically for the ACI on what we can turn on and off for the strength limit state. So for example, we're going to see here strength reduction factors, some minimum and maximums to consider directly from the standard. Now the stability tab here is related to the moment magnification method. We're not running that for today, so nothing to take care of here. As far as the serviceability configurations, if we take a look at this, you'll notice initially we're going to be checking the crack analysis. So what this is going to be allowing us to do is to take into consideration section 2432 from the ACI to make sure that our spacing of our longitudinal reinforcement meets the code requirements. Now, additionally, we can turn on the direct crack width calculation. This is a bit more of a theoretical approach. It will utilize the Gurgley-Lutz equation to calculate the crack width. We can compare this to the reasonable crack widths set forth by the ACI PRC 224. So directly from that standard, we have some different options here that allow us to choose our limiting crack width. For example, dry air protective membrane, we can set this to 0.016 inches. Some minimum longitudinal reinforcement due to shrinkage and temperature. Then we have our deflection consideration. So the limiting deflection ratio for our members is going to be set here within these configurations. If the member is supported on both sides, we have a value here, limiting ratio of L over 240. For cantilevers, we also have L over 240, but you can modify those here. Long-term deflection is controlled here. So when this is turned on, we can choose the time-dependent factor according to table 24241. This just applies a simple factor to the deflection analysis according to the ACI. Alternatively, we can consider creep and shrinkage here according to ACI 435. Now remember, I showed you the material properties itself allow you to define those creep and shrinkage properties. We'll go ahead and turn that off for today. We won't be considering long-term deflection, and we are done with the configurations here. Now, the final tab is related to our design supports, and this is important for two different reasons. The first we'll start off with is deflections. So the program doesn't know which portion is supported on both ends, which end is a cantilever. So by defining these design supports, that gives the program the intelligence to recognize which limiting deflection ratio to compare the different segments to here. And what we'll begin with is a new design support at the left-hand side. So I create this new design support. You'll notice the type is set to concrete. We give it a support width of 16 inches. The support depth is just set to the width of the member. We have a nice picture over here on the right-hand side, just referencing what some of these settings are. Now we also have the ability here to reduce the moment. So we can set this factor for a moment redistribution over this support width. Now this is all related to the ACI section 665. So when we create that support width, we can automatically see it set here on our first node of our beam. Now we also want to set that design support on the intermediate node along the member length. So we can do so here at node number 3 by either selecting the support we already defined, or we can create a new definition. This one will also be 16 inches in width, but I want to set my ratio here, maybe 0.75. I click OK, and now we can see that nice design support shown here. So now the program will have the intelligence to recognize this is a cantilever portion out here on the right, and this portion here is supported on both sides. Now, if you do not set any design supports within this tab at all, the program automatically defaults to a support at the member start and the member end internally. Now, these design supports are also important for a second reason, and this all comes to do with strength design when we're talking about topics like taking the shear internal force a distance d away from the support face. Well, this will all be considered now with these design supports that we've defined. Otherwise, of course, the program only knows the intelligence of taking the shear force, for example, a distance d away from the member start. The information over here on the right is just related to the serviceability deflection checks. We can add in a pre-camber. We want to tell the program what is the reference length for our limiting deflection ratios, and that will sum up this particular tab here. Okay, so now that we have finished all of these various settings, notice that the program has automatically updated my reinforcement. We can see those design supports shown here, and we can now move on to the design utilizing the concrete add-on. So within my table down at the bottom, I'm going to activate the concrete design here. So this is available because I have set this under the base data to turn on that concrete design add-on. Under the first tab, here are my two design situations, LRFD and ASD. We need to tell the program to use the LRFD according to this drop-down box for strength design. Now we want to use the ASD or unfactored load combinations, utilizing this drop-down box for serviceability design. Now notice we also have an additional option here for seismic design. We could create a new design situation. We could select seismic design as well. Currently, this is only for reinforcement seismic detailing according to Chapter 18. So we're working on establishing some more features there in Chapter 18, but that will be coming in the near future. So for now, just looking at strength and serviceability. Now the objects to design, we can see here we only have one element in the model, of course. The rest of these tabs are really just repetitive. It tells us our materials, our sections, so nothing to really do here. So we can begin by running our calculation directly within this table. Now notice that the program will run through our load combinations here, and it's also running through the design portion. It solves pretty quickly, and we can see now we are presented with our results. So we're still within this concrete design add-on, and now within the drop-down box, I can look at my design ratios on my members. And here they are grouped together quite nice, showing the strength design, the serviceability, the reinforcing limits, and the detailing of the reinforcement. All of the design ratios here are green. That's always a good sign rather than seeing red, which means we're over the design ratio of 1.0. We can also utilize these factors or these filters up here at the top. If we wanted to view maybe only the max ratio, we can select the max here. Otherwise, all of them will be shown. Now notice as I click through this, the big red arrow showing in this graphical interface here will determine where my controlling internal force is. The other new thing within RFEM 6, for any one of these design ratio checks, what I can do here is to visit my design check details. So this is going to launch this dialog box that is going to show all of my code equations here. So notice this one is pretty long and complex, but we show every single equation. Down at the bottom, we're going to give you every variable definition. We're also giving you all of the code references along the side as well. So we can use any one of these checks here. Currently, we're looking at serviceability. We can take a look at any one of these other checks to determine the ratio here for our other various serviceability checks. Now, alternatively, we can take a look at any one of the strength design checks as well. Same concept. We're going to see all of those variables listed again with all of the code references. What else is pretty powerful is we can view the diagram in section. And this is showing me which portions of this concrete section here are in compression, which are in tension, and we're also giving you the stresses for each of the rebar here. So this information is all available to us, of course, in our table format, but now we have this new drop down here for concrete design. And we can see if we collapse these trees that we have two options here, the design checks or the reinforcement. So let us take a look at the design checks first. Also, I can turn off my reinforcement on my member by visiting my navigator display options. And here we'll see types for concrete design, and I can turn off my member reinforcement. So going back to my member design check results here, I can turn off maybe the max ratio and turn on any of the various checks related to my color coding here, which all relate back to the table design ratios. Now, in addition to viewing the design checks, we also can take a look at the reinforcement along the member. And what I mean by this is we can view the required reinforcement at the bottom of the member. This is strictly from the analysis. Well, on top of this, what we can do is to overlay the provided reinforcement on the bottom. So what we would always hope to see, of course, is that the provided reinforcement is greater than the required reinforcement. And in a similar fashion, we can turn on the required reinforcement for the top, which makes sense. We see it over here along the support and into the cantilever. What we can do is to overlay the provided reinforcement at the top. And again, this is greater than the required. So some various options there in terms of how to graphically view these results, these concrete design results, both in table format as well as within the graphical options. So that will go ahead and wrap up our first example here. I wanted to give you an introduction to just a simple beam design. For our second example, let us move into a little bit more of a complex structure. So now we have an entire building here. We have columns, beams, walls, and slabs all defined with reinforced concrete. Now, the first thing that I want to do here is I've already loaded, set up the load combinations, taking care of a lot of this information that we just did with example 1. Let us go into our design situations that we already covered. So again, we have LRFD and ASD, and as we mentioned before, we need to set those I crack factors for our factored load combinations for the strength design. Well, I went ahead and did so. I just want to show you guys how this differs a little bit when looking at the structure modification here. Now you'll notice I've activated both members and surfaces. We have two tabs up at the top, and I have set the I crack factor for my columns. I've selected all of the column members here. I also see my beams, and I've selected all my beam members. And under my surfaces, we have set the I crack factor according to the ACI for walls uncracked and flat plates and flat slabs. Now, just to go into these detail settings, I also wanted to mention that in a similar manner, we have the Canadian standard here. It's the same concept for designing according to the CSA standard, so that option is also available here. Okay, so now that we have defined these structure modifications for our factored load combinations, I created an additional combination wizard for my unfactored load combinations, which should not have any stiffness reductions. So we'll see that reflected here within our load combinations, just like what we saw with example 1, but now we have many more elements. So let us begin with the reinforcement definition for our first surface. And we'll choose this slab located here in the center. And I will go ahead and create a visibility by the selected objects. I'm also going to right click on this surface and I'm going to turn on the local axis system. Turn this to wireframe view as well. The local axes are important for the reinforcement directions, which we'll see in just a minute. So I wanted to go ahead and set us up for that. So all we need to do is to double click on the surface here. Now, just like with the members, with this design properties turned off, which is the case with every single element within this model right now, we're only running the analysis. But when I activate the design properties, we see all of our additional tabs here where we can define our reinforcement for the design. So let us move to the concrete cover. And we'll begin by defining a new concrete cover of 0.75, just referencing at table 25131 from the ACI. And let's see, sorry about that. Okay, now the concrete design properties. This is going to be where we set our reinforcement direction. And we have no reinforcement direction defined right now, so let's create a new one. The reinforcement direction is going to be related either to the local x-axis or the local y-axis of the surface. So this is why I wanted to turn on the local axes so you can understand how the reinforcement direction is influenced by this. We'll begin with the local direction x for the top side as well as the bottom side. So if I bring this down again, we're utilizing the direction based on the local x-axis, and the transverse direction would be the local y-axis. Now, of course, you can rotate this too. It doesn't necessarily have to be in either one of those orthogonal directions. For the surface reinforcement, we create a new definition here. And we're going to apply the reinforcement over the entire surface. My reinforcement material is already set at grade 60. The reinforcement type can be welded wire mesh. We have the library in there. It can be rebars or it can be stirrups. So perhaps we want to define some additional shear reinforcement around our columns, for example. But we'll go ahead and utilize the rebar option, and we will choose number 5s at 12 inches on center or 1 foot. Now we also want to apply this in the transverse reinforcement direction. So notice right now it's only spanning one way. When we activate this, we want to choose number 5s, spanning 1 foot in the orthogonal direction here. So we see the picture update over here on the right. Now we're applying this to both the top and bottom of the surface. So I've created this first definition type here. We can see it populate here within our table. Okay, so the design configurations, really same concept here of what we just talked about with our first example. Just notice that we now have an additional tab here for surfaces. So just some various settings specific to the ACI for our strength limit state design. Serviceability, same concept we've already discussed within the previous example, but just know that we can check deflections for surfaces as well. So that limiting deflection ratio is still referenced here within this design configuration. Under the last tab, deflection, this is where we simply tell the program, is this surface supported on both ends or is it a cantilever? The reference length is determined by this dropdown where we can use the maximum boundary line of the surface, the minimum boundary line, or we can manually set that length as well. So now that we have defined our surface reinforcement here, we can click OK, and we see this graphically update here with our number 5s at 12 inches on center. But if I go ahead and right click and show the hidden objects in the background, we know that we have these columns framing up into the slab here. So we're probably going to have some additional negative moment at these locations. So perhaps I'd like to add some additional top reinforcement, but only at these locations. We don't want to apply it to the entire surface. So if we take a look back at our navigator here, we see the types for concrete design. And here's our surface reinforcement. That surface reinforcement number 5s at 12 inches on center is defined within this tree option. Well, I can right click to create a new surface reinforcement, and this dialog box should look familiar, but this time we're going to choose the option free rectangular. So here we can define additional rebar, and I'm going to choose again number 5s at 1 foot on center. And I'm going to also define the transverse reinforcement, number 5s at 1 foot on center. I only want to apply this to the top of the surface, not the bottom. Now, we could take this a step further and apply an additional offset here. So perhaps we wanted 2 layers of reinforcement within our concrete slab. If we do not define any offset, the program is simply going to apply this area at the same location as my previous surface reinforcement that we can see as item number 1 here. The direction and location tab, I'm going to choose the option center and sides of rectangle. This allows me to graphically choose my point here, and I'll choose the top of one of these columns, 18 and -11. I define the size of my rectangle, 6 feet by 6 feet. And then I can graphically choose my surface here I'd like to apply it to. Now, this picture represents the fact that we can actually project down this reinforcement over multiple levels. So if we have a multi-level story concrete structure, and we know that this same free surface reinforcement should be applied at every single level, we can define multiple surfaces here, and the program will automatically place that at every story level. Okay, so once we click OK, we should see that additional reinforcement here. Now, it might make a little bit more clear under our display navigator. I am going to turn off the surface reinforcement here on the surface itself, so we only see this rectangular surface defined here. Additionally, what I can do is to select this, hold down my control key, and actually just drag and drop it to different locations on my model that I know I'm going to have a little bit higher of a negative bending moment. I also have some areas back here where we kind of intersect with the walls and columns that need a little bit more reinforcement on the top. So of course we'd want to continue optimizing this best we can based on the internal forces. Again, we probably want to add some shear reinforcement and such to the slab. Now, just taking you to another little side note here, punching shear, this will be ready actually, hopefully in several weeks for the ACI. It wasn't quite ready for this presentation, so we're not checking that right now, but that should be very close to being done within the program. So once we have defined our surface reinforcement, we can actually begin the design. But before we do, I'd like to define a little bit more reinforcement for some of these other elements within the structure. So let me turn off the free rectangular, and I will turn off the local axes of the surfaces, and I'll cancel this visibility mode and turn this back into the rendered building here. So notice we have these beam elements drop below the bottom of these slabs. Well, these are special members. If we double click on them, the member type is set to rib. So what a rib element allows us to do is to actually design this as a T-beam, so integrating it into the slab directly. So what we do is define the rib alignment here on the -Z side of the surface. Now, what's new within RFEM 6 is that we allow you to vary the effective width or the flange dimensions along the length of the member. So currently the default is just L/6 over the full length of the member. But what we can do here is to change this to maybe 85%, and we'll modify this to the segment, and we will set this to L/8 instead. Now from 85 to 100%, I'm going to use my definition type here to user define. We will set this to 6 feet, and we will go ahead and select L/8 once again. So notice that the effective width transitions clearly here at 85% to a smaller value. Now, what else is new is that we have this option within the distribution linear column down here at the end to linearly distribute this to the end. So notice at 85% to 100%, we have a clear line transitioning back to the end of the member. So this is all done as we approach the interior column here. So that effective width is set for that rib member. Now I went ahead and did it for the rest of these members. You'll notice here for this particular rib section, if we zoom in, we have this linear distribution at both ends as it spans between these interior columns. Maybe up at the top though, we want to also utilize these rib options, but for these, what I went ahead and did is just set these without using that distribution option down at the end. So we have a clear, distinct view here of where the effective width changes at 85%. So either are possible within the program. So let us begin by designing this rib member here in the center of that lower level. Now remember, everything has been turned off for the design property, so we want to activate that now. And we are going to take a look at the concrete cover. Remember the effective lengths we leave empty. We're not designing according to the moment magnification method, but rather P delta. The concrete cover, we will leave this as default at 1.5 inches. Now for my shear reinforcement, I actually do want to have 3 different zones here. So I can zoom in, and for my first zone of my shear reinforcement, we want to choose number 3s, but we'll go ahead and have a tighter spacing here of 4 inches or 0.33 feet. Now I want to modify the distance here of this zone so that this is applied from 0 to 3 feet. And now we can see our picture update down here at the bottom. My second zone is going to be number 3s, and we're going to modify this spacing at 0.5 feet or 6 inches. This will be applied from 3 feet to 12 feet. And finally, for our last zone, we want number 3s at 0.33 feet. So that will be that 4 inches there. And this will be applied from 12 to 15 feet. Again, everything is updated within this picture. For the longitudinal reinforcement, notice we have some grayed out options here. So what does this refer to? Well, if I take a look along the length of the member, we can actually consider automatically the surface reinforcement. Remember those number 5s at 12 inches on center that we defined? You can see them displayed here in the effective widths or the flanges. Well, we can also turn this off and to manually apply reinforcement as well, which is what we'll be doing today. So we'll begin first with the basic longitudinal reinforcement here within the main member. For this one, we can keep this as symmetrical. 3 number 6s are fine here. Again, this is applied along the full member length. So let us create a new item, and this option will be set to line. And for this line option, we want to choose 4 number 5s. Again, our offset type will be from the stirrup. Now within my drop-down options here for my offset distance, we want to modify this to left positive Y and top positive Z. Then we can adjust our offset distance to -1 and 0, and we can see that the reinforcement begins to update here. Okay, so the other thing that we want to go ahead and modify is the right distance. This should be right -Y, which we see here, but top positive Z. We want to go ahead and modify this one to a distance of 1 and 0. And if we kind of expand here on the distance to get maybe a larger effective width here for our flanges, this will make a little bit more sense as we see our reinforcement on top. So definitely have to play around with this in order to possibly get those offset correct with the display options. This will also be applied along the full length of the member here. Okay, so design configurations, we've already covered. The design supports. Again, I had mentioned if we do nothing within this particular tab, the program will just treat it as supported at both the member start and the member end. Perhaps we'd want to take into consideration the fact that this rib is framing into the column. So we'd want to set those design supports here. But for our example today, we'll go ahead and leave that empty. Now we should see the reinforcement drawn graphically here within the model. Okay, the final thing to do is to set the reinforcement for some of the columns. And for this, I want to go back to my navigator here. And I'm going to right click to visit that base data. So if you remember when we began our example, we can revisit this dialog box here. And under these settings and options, I can activate what's called member representatives. Well, up pops a new tab up here at the top, and what the program has the ability to do is to group together members based on similar materials, sections, lengths, and so on. I've also activated comments here. So what we'll see when we click OK is a general color coding here of all of those elements grouped together that have those similarities. Now, the columns at the first floor are actually identical to the columns at the second floor. So how I differentiated them is just to simply type in this comment down here at the bottom for those members, second floor, and then automatically the program will place them into a different member representative group. And we can see this denoted by this green color. So what I can do is to double click on the green color itself, and up pops all of our member representatives. So we'd like to define the reinforcement for the columns. Well, currently members are listed here, and I'm going to go into the edit settings. And I have the design properties turned off, so we're going to turn those on. Now, I'm not going to define the reinforcement here because if I do so, I'm actually defining that individually for each member. Rather, when I click OK, you'll notice that I'm still within the member representatives, but now I have the exact same tabs available to me here. Why this is beneficial, if I go into my member representatives, I make a quick change to the reinforcement, that's going to update all of my members that are grouped together. So once again, we will visit the concrete cover, 1.5 inches, the shear reinforcement. We want to modify this here. We'll just go ahead and change the spacing to every 6 inches, 0.5 feet. We see our picture update here. The longitudinal reinforcement, we're going to use our drop-down box to choose uniformly surrounding. And we're going to choose 8. Number 6 is here. We can see again, the picture updates accordingly. These are applied to the full length of the member. I click OK, and what we should see now is all of our reinforcement for every one of those columns at our second floor. So now that we have defined the reinforcement for the surface, for this rib element, for the columns, let us move into running the calculation for both the analysis and the design. So remember, we want to utilize this drop-down box here to visit our concrete design add-on for the input data. LRFD, our factored load combinations, are going to be set according to the strength design. Our unfactored ASD load combinations are set according to the serviceability design. The objects to design. Well, we have a lot of red elements here, and that is just simply because we have not defined the design properties. I didn't turn on that checkbox. I didn't set the reinforcement. So therefore, we're going to get errors if we try and design everything within the model. So rather, let us turn off these checkboxes here, and I'm going to graphically select surface number 19, and then I'm also going to graphically select my rib element here. And I can also utilize my selection box here to choose all of my columns at the second floor, and I click OK. So now only the relevant members and surfaces will be designed here. The rest of these tabs down at the bottom, we discussed that is just a little bit of repetitive information, nothing to do further, and we will begin the calculation. So new within RFEM is utilizing the multi-core processor within your computer. Notice that these load combinations, both the factored and the unfactored, are going to solve at the same time, even for these larger models such as this building. Previously in RFEM 5, we had one solve after the other. So these are all complete. Now notice under the concrete, we have to solve again all of the unfactored load combinations. And the reason for this is, remember, we talked about the effective moment of inertia, I sub E, and that is related to the ACI table 24235. The program automatically calculates that stiffness reduction to be considered for the serviceability deflection checks. So that's why we're seeing those load combinations listed again here. Now, the final progress bar is just going to be showing us how all of this information is compiled into the table format as well as the graphical format here. So this should solve in just a couple more seconds, and we will be back in RFEM with the results. Okay, so now that this is complete, what you'll notice here is we are viewing the overview from the concrete design. So any errors, any ratios that are greater than 1, we would see that listed here. So let us jump down to the design ratios on the surface. And it actually doesn't look too bad. Everything looks green except for, of course, the shear resistance. Inevitably, which I can go ahead and show this to you guys here, the reinforcement on the members is just simply needed for these areas where we have the column intersecting with the slab and at some points where the wall is intersecting as well. So what we'll see listed here otherwise is the design ratios for strength, again, reinforcement limits and serviceability. Now, for these checks, we can visit the design check details, and similar to what we saw with our member design, it's a similar concept for the surfaces. This one you can see is rather complex, but all of the code references, the equations are listed here. We can also utilize this drop-down box if we want to jump to one of the other design checks here. This one's a little bit more simple, again with the code references given to us on the right-hand side. So very similar, again, to what we saw before with our members. What I did want to show you is also the graphic options here for our surface. So what I can do is to go ahead and set the visibility by the selected objects, and let me collapse my results here. So first of all, we can view those same design checks on my surfaces. Notice here, if we go ahead and turn on all ranges here within the surface, where our problem areas are for each one of these design checks. Again, similar information to what we saw here within the table format. So in addition to the design check ratios, we also can take a look at the reinforcement. So we want to take a look at the required reinforcement. Let's say for our surfaces here, this would be the top reinforcement in direction 1. And we can also view the top reinforcement in direction 2, as well as the bottom reinforcement, some various options here. So similarly with the members, we have the results available to us in the table format. So let me cancel my visibility mode here. And let us move to our drop-down that shows us the design ratios on the members. So currently we're viewing this tab, design ratios by member. Notice that when I click in here, we're shown exactly where that controlling internal force is for this particular column. I'm not going to spend too much time going over the results because we've already seen this with example 1, but with our columns, what might be interesting to us is this new feature here within RFEM 6 for our interaction diagram. So this was long awaited, and we're very happy to present this now because we will see the interaction diagram available to us with this new tab and the 3D view here. So we can view all of the values within table format, but we can also see where exactly we land within this interaction diagram for this particular member at this X location. We can add this information to our printout report, so very powerful there as well. And of course, we have our design check ratios, our reinforcement that can all be shown graphically for the members that we covered in the first example. So the final thing to cover is just a quick few options with the printout report. So what I'll do is to create a visibility here for my surface. And I want to hide these hidden objects in the background. I'm also going to adjust my view here to the reverse Z direction. For my reinforcement, I want to show all 4 of these options here for the required reinforcement in my printout report. So the first thing I'll need to do is to actually generate the printout report itself. Well, up here in our toolbar, we can choose New Printout Report. And we can see all of the various settings we can turn on and off within the model. Now, we also have some saved templates here. So you can load one of those saved templates, or you can create your own template. We'll go ahead and work with template number 1, input data and reduced results. So I click OK. I click OK once again. So that printout report is now created in the background. For my graphics, I'm going to choose my drop-down option here to print the graphics to the printout report. And what we'll notice is that I can set this to the full page height. And I've set this to the window filling so that it is nice and zoomed in here. And I don't want to just print this view here, but I want to take advantage of what's called the multi-print. So when I select this option, I now can visit this tab up here for my concrete add-on. Now, all of the various options available to me here is exactly what we have available in RFEM that we covered. So what I'd like to do is to activate for my printout the required reinforcement in both directions for the top and the bottom. So I click OK. And then what I should see down in the lower left-hand corner is the progress bar that has now added that to the printout report. So if I go back to my navigator here, I can find that printout report available to me here. I can double click on it. It should go ahead and compile all of those results. We can see our progress bar here to open up the printout report in a separate application. So we can see that application load, and I'm going to collapse our report navigator chapters just so it's a little less overwhelming here on the left-hand side. But this is going to show us, and I can zoom in here, all of the input data, including the results for our structure. But down here at the bottom are those 4 pictures that I just printed off based on that multi-print option. Now, what's really powerful is that if I make any changes to this model, the program will automatically update these pictures. So we don't need to go in and print them again. So once these pictures have been defined, what I can do here is just to drag this printout report to my other monitor, because we can work concurrently in the program at the same time. So let me cancel out this visibility mode, and I'm going to go back to my results here, turn off my surface, and I'm going to select only my rib member, and I'll create a visibility by the selected objects. Additionally, I'm going to turn off that member reinforcement here, and we will choose our view in the Y direction. So just a simple wireframe view of that member. Well, back under my results, I'm going to take a look at the design check ratios for this member. And I don't want the max, but rather I'm going to overlay here several of the design checks. And you can see again, these color codings will show me exactly which design check ratios I'm looking at. So let us print this off to our printout report as well. So I go up here to choose print graphics to printout report. And this time though, we want to view the current view only. And I want to also modify this to not the full page height, but we'll choose 50% of the height. So once I have these settings correct, I click OK. And what I'll do is to drag this printout report over to the monitor so that you all can see it too. And we now have this picture automatically added to the printout report. Now we also can right click on any one of these folders to create a child folder. So perhaps we want to rename this to Surface Graphics for a little bit better organization. I can right click under Concrete Design, create child folder again. We'll call this Member Graphics. I click OK. And I can use my shift key to select all 4 of my surface options here. I can drag and drop them into that new child folder, and the report will automatically update. For that rib picture, I can drag and drop that one into member graphics, and we can see here it's now added to that portion of the printout report. All of this information you can edit, including the logo, the cover page. We can modify this cover picture. Once you have the information set the way you like it, definitely save it as a template, and you can use that for any future models within RFEM. So extremely powerful printout report. We did a lot of great changes with this new version. So certainly take a look at this. Okay, so we are ending the hour today, so I'm going to go back to the webinar. One thing I just quickly wanted to mention before concluding the presentation is just some upcoming developments. So when we're looking at the ACI, I had already mentioned that punching shear should be ready in the next several weeks. So that will be something that we can look forward to. Chapter 18 for seismic design. We currently have the reinforcement detailing available to us, but we're going to continue expanding on these topics, including information like strong column, weak beam. The 2014 standard should be implemented relatively soon as well. RFEM 6 was completely rewritten in an updated programming language. So we initially started off with the most recent standard, the 2019. We'll go ahead and add in the older version as well. And nonlinear concrete design is also in development. So this can actually consider the true crack cross-sectional properties for members and surfaces for that nonlinear design. CSAA 23.3, everything that you saw today is also available for the Canadian standards. It's an identical workflow. We're just doing the design according to the CSA. The punching shear, that should also be available soon according to the Canadian standards, and nonlinear concrete design as well. So these are just some developments in the near future. Of course, we have longer term developments as well that are just a little bit further off. So I know that was always quite a bit of information. This webinar is recorded. It's placed on the web page that you registered. You can also download the models that I used today. You can download the trial version, its full capability for 90 days, including all the add-ons. So you can open up the models you saw today, follow along with the webinar to continue learning. If you have any questions about today's presentation or any of our products, you can reach us in our Philadelphia office with our contact info shown here down at the bottom. Our phone number is 267-702-2815, and our email is info-us@delubal.com. We will have many more upcoming webinars, especially as we continue to introduce you to all the new features and developments within RFEM 6. You can register at delubal.com under support and learning webinars. And most of you know I send out a reminder email about a week before this takes place, so keep an eye out for that. PDH certificates will automatically be emailed to all participants who were here for the full presentation. So this is a requirement by the states that we are pre-approved providers, that you are here for the full 60 minutes, so you can expect to receive that PDH within the next day. If you watched with a colleague or you watched in a conference room type setting and you yourself did not register for this webinar, but were here for the full presentation, please request that PDH at info-us@delubal.com. So again, if you yourself did not register with your own name, your own email, and you watched with a colleague, please let us know who you watched with and request that PDH again at info-us@delubal.com. And with that said, I want to thank everyone for attending, and as always, we hope to see you at the next presentation. Thank you.